Well, hello again. We're going to take physics in a little bit different direction from all the mechanics that I've been doing in previous videos. And we're going to look at internal energy of an object, basically the motion of the molecules of an object, even when the object itself doesn't appear to be doing anything. You know, a rock sitting on a table doesn't look like it has any kind of energy, not potential, not kinetic. Well, maybe potential if you set the zero level someplace other than at the table. But the molecules all have energy. They're vibrating, moving back and forth, which means they have at least kinetic energy, and they're kind of bonded together, which means they have a kind of potential energy also. Think of a spring that's being compressed and released all the time. And that's the kind of energy we're going to be talking about. But we're going to be talking about it at the macroscopic level, that is large amounts of energy, the aggregation of the molecules rather than individual molecules. Different kinds of internal energy would include, for example, thermal energy. That's basically what we're going to be talking about, but there are other kinds I want to be mentioning here. Thermal energy changes as the temperature of an object changes. If the molecules are moving faster, they'll have more kinetic energy and the temperature will be higher. That's what I mean by a macroscopic measurement. We can measure the temperature. We can't see the molecules moving or measure their speeds, at least not directly. The different kinds of thermal energy then would be potential energy. As I mentioned, the molecules could be bonded to each other. Translational kinetic energy, that's this Ke sub T thing right here. That's talking about objects that are moving back and forth and bouncing off each other. And rotational kinetic energy, that's Ke sub R. Now, the rotational kinetic energy can happen if the molecules are not monatomic. And what I mean by that is this. In a monatomic gas, like what we have on the left side here, the molecules are basically just atoms. This would be like helium, for example, and other noble gases. A diatomic gas, such as hydrogen or oxygen, those molecules can rotate. And when they rotate, they will have a kinetic energy, as well as moving in straight lines, which would give them translational kinetic energy. So that's what I'm talking about when I'm talking about thermal energy. Other kinds of internal energy that we're not really going to be discussing would include nuclear energy. That would be within an atom. In fact, inside the nucleus of an atom. Strain, that would be like, for example, if you take a meter stick and bend it, it has a different amount of energy than when it's unbent because it has that potential energy to return it back to its original shape. And chemical energy. And for that, you're talking about the interactions of different atoms with each other and their electron shells. Talk to your chemistry teacher about that one. But we're going to deal with thermal energy. So let's suppose we have a tank of gas. Okay, we have a gas in here, gas. And let's suppose we have a movable piston up here on the top, and we apply a downward force on it, and we move the top a distance of delta Y. So essentially we're compressing the gas. As the molecules bounce off of that top as it's moving down, they will bounce off faster than they hit it because it's moving down. Think of a ball hitting a baseball bat. If it's hitting the bat and the bat's not moving, it bounces off at approximately the same speed. But if the bat is moving, then it bounces off faster, and that's what happens to the molecules. They'll be speeding up as the top moves downward. We're doing work. The work done on the gas is, of course, force times distance. So I have force times delta Y, but force is, as you know, pressure times area. So it's pressure times area times distance. Now you might be wondering about that minus sign right there. That's just to keep the work done on the gas. I'm being specific here, on the gas. That's keeping that positive. What? Well, yeah, because you see delta Y is negative. You see the size of the gas is shrinking. So we call this a decrease in the height of the cylinder. So if this is negative, then we need a minus sign over here to make the whole thing positive. Got that? So there's our formula for the work done on a gas. Now, of course, this depends on the pressure not changing. If the pressure is changing, then we've got a little bit more complexity to the problem, and that's going to call for calculus. So that is, wait a second, where did this negative P delta V come from? Well, you see here when I change the force into pressure times area, right here we have area of the top times the distance it moved, we talking about this little cylinder right here. That's the volume right there that changed. Okay, the area of the base times the height. That's the volume of a cylinder. So this is negative pressure times the change in volume. And that's the work done on the gas, or in other words, the work done by the environment, say someone's hand pushing down on the top of the cylinder. So to summarize that, the work done on the gas is the negative of the pressure times the change in volume. That's an important theorem, so you need to write that baby down. And again, that assumes that it's being done at constant pressure. If the pressure is changing, by the way, for you fans of calculus, if you just have to know, then the work would be negative the integral of the pressure times dV. If that makes sense to you, great. If it doesn't make sense to you, don't worry about it. It will someday if you need to know it. So that's the work done on the gas, or the work done by the environment. Basic ideas then. If the work done on the gas is positive, that means the volume has decreased. Okay? And that means that the work is being done on the gas. If the work we get is negative, that means that the volume increases, because in order for this to be negative, delta Y would have to be positive, which means this lid would be going up. So the volume would be increasing, and that means that the work is being done by the gas to push the lid up. Got that? Okay, good. Thermodynamic processes. That's the key to what we're talking about here. Two parts to it. Thermo has to do with heat. Dynamic has to do with change. And so we're talking about changes in a gas related to heat. There are 4 of them. One kind of change is called an isovolumetric process, or isochoric. And what that means is that there is no change in volume. But of course, if there's no change in volume, that means that the lid of the container didn't move, so there was no work done. How can you have a no volume change process? Well, have a sealed container and heat it up. Okay, you've changed the internal energy of the molecules, but you haven't changed the volume, so you haven't done any work. Okay? You can also have an isothermal process. Isothermal means that there is no temperature change. That is, delta T is 0. If there's no temperature change, that means, assuming that you kept the same amount of gas, that there is no change in internal energy. Delta U there is what we use for the change in internal energy. That's what U is right there, internal energy. Internal energy. So if the temperature doesn't change, neither does the internal energy. An isobaric process, do you know what a barometer is? That's right, it measures air pressure. Isobaric process means that there is no pressure change. So the pressure doesn't change. It doesn't say the pressure is 0. It says that the change in pressure is 0. So that means the pressure is constant. Make sure you understand that. And finally, well, this one looks different. What happened to all the isos? An adiabatic process. You like that word, adiabatic? Use that around the dinner table. Impress your parents. Means that there is no heat loss or gain. Q is the symbol we use for heat. Okay? And so no heat loss or gain is not the same as no temperature change. Heat is measured in joules. Temperature is measured in Kelvin. 2 different things. Obviously, they're related to each other, but they're not the same thing. So let's suppose we look at this. This is called a PV diagram. See if you can figure out why. Okay, I think you did. We have 2 processes. Maybe we'll call them process 1 is right here, where the pressure goes from a high pressure to a low pressure, but the volume's not changing. And process 2 right here is where the volume goes from a low volume to a high volume, but the pressure is not changing. Which process is isobaric? If you need to go back and review, pause the video and do that. But I'm going to move along here. Isobaric means no pressure change. Just think barometer, and that is process number 2. That has no pressure change in it. It stayed right there at P sub F. Which process is isovolumetric? Well, that's the one that, let's see, has no volume change. In process 1, the volume did not change. Okay? How much work was done in each process? Well, again, pause the video if you need to, because I'm going to reveal the answers. I'm just that way. I tell all. In process 1, the volume didn't change, so no work was done. So for process 1, the answer is 0. Process 2, the volume did change. And so for process 2, we just use our formula. Since the pressure is not changing, the work in process 2 is negative P delta V, but delta, remember, is final minus initial, so that's V final minus V initial. Now I want you to notice something. Final volume here is bigger than the initial volume, so this is positive, which means the work done is negative. That means that the gas expanded, and sure enough it did, and it means that the work done on the gas was negative. That is, it was the gas that was doing the work. It was expanding into its environment. It was pushing the lid higher. Okay? The absolute value of the work, whether it's positive or negative, is always just the area under the PV graph. That is, if we found this area right in here, wouldn't that be the change in volume times the pressure? So that area under the PV graph gives you the amount of work that's done. Okay? All right. Now, that's an important concept because not everything is made out of nice horizontal and vertical lines. Some processes involve diagonal lines, and some of them involve curved lines. But that idea that the work done is the area under the graph will always be true. So let's look at a graph like this. We have an initial high pressure, a final low pressure, an initial low volume, and a final high volume. What kind of process do you suppose this is? Where the pressure decreases as the volume increases. That seems familiar, and you may have seen that in chemistry class. That is called the isothermal process, where the temperature stays the same. Back in chemistry class, you learned something called Boyle's law. You might remember that it says P1V1. We'll call it P initial times V initial equals P2V2. That is pressure final times volume final. That look familiar? But, and this is the big key, that's true at constant what? At constant temperature. And so that's where we have our isothermal process, and this is what it would look like. That's Boyle's law, an isothermal process. If you wanted to find the work that's done in going along this path, you'd have to figure out a way to come up with this area right here. And again, that's where the rules of calculus would come into play if you've taken some calculus. Got that? Okay, that's your introduction to thermodynamics. I hope you understood it, and there'll be more in the next video. Thanks.